Okay, welcome to our session for today. So I'll discuss your previous quiz on determinacy and getting the reaction. So we had already known the criteria on determining the determinacy of beams, frames, as well as the trusses. So for this problem, starting with this one, we have for beam, we have to compare our R to C plus 3. Okay, so counting the number of R, we have here one reaction, two reactions here, and of course this cable is counted, so therefore there are 4 reactions all in all. And for our C, this is the coefficient of internal reaction, so we have for internal roller we will use 2. So by this, R is 2 plus 3, and then we have 4 is less than 5. So if this is the case, we will conclude that this is unstable. So next, we have here a prop beam, and then on the edge it is supported by a hinge. So similar, we will count the reaction and compare it to C plus 3. So in here, in this fixed connection, there is a vertical, horizontal, and a couple. And for this one, we have 1. And for the hinge, we have 2. So therefore, 3, 4, 5, 6. So the count of reaction is 6. We do not have any internal reaction coefficient. So therefore, R now is being compared by C plus 3. So this is 6, 0 plus 3. Therefore, 6 is greater than 3. And then the excess is 3, or 6 minus 3. Therefore, this is statically indeterminate to the 3rd degree. So for the next problem, again, we have here a fixed end supporting this beam. So please do not count this one because this is just a support for the cable. Our concern is the determinacy of this beam. So we have 3 again for this fixed support. We have 1 for our roller and a count for the cable here. So therefore, the reactions, we have all in all total of 5 reactions. And again, we do not have any internal support. So C is equal to 0. Therefore, R is C plus 3. Then this one, 5, obviously is greater than 3. So we can say the excess, having a 2 excess here, 5 minus 3. Therefore, this is statically indeterminate to the 2nd degree. Okay. So for the next problem, we have this beam supported by a hinge here, another hinge, and 2 rollers. So if we are going to load this one, of course there will be a mechanism of instability here because this joint will swing or rotate, whether clockwise or counterclockwise. So there's no mechanism of restraining or restraining rotation here, because it will rotate at this point, and certainly it will also rotate at this point. So with that, without having the criteria, we can say that this beam is unstable. Okay, so next problem, we have a fix on both ends and an internal pin here. Although it is free to move, again it will be restrained at both ends. So we cannot say that this is unstable. We need to count the number of reactions and then apply the criteria. So for the fixed end, we have 1, 2, and 3. So another 3 reactions at the other support. Of course, C for an internal pin is 2. We multiply it by, so C for internal pin is 1. We multiply it by 2. Okay. So we also have 2 reactions for the external pin there. Now comparing now the R to C plus 3. So our count is 3 plus 3, 6, plus 2, 8. And then we have 2 plus 3. So 8 is greater than 3. 8 is greater than 2 plus 3. 8 is greater than 2. 5. 8 is greater than 5. So therefore the excess is 3. So therefore this is statically indeterminate to the third degree. Okay. So for the next problem, it is obvious that all of the reactions will be concurrent at a certain point. Say this is the point, okay? So therefore, we do not need actually to count the reaction, just simply conclude that this is unstable, because that criteria of having a reaction that is concurrent at a certain point, that will be unstable. So for the other beam, of course there will be 3 reactions here, and it is very glaring that we have a parallel reaction here. So when we have a parallel, it says that it is unstable. Why? Because if we're going to load a lateral load here, say this diagonal will have a lateral load that will tend to slide this horizontally along the right direction. Of course, there is no reaction. There will be no reaction to counter this rightward force or any horizontal force that will be applied here in the beam. That is why this is automatically unstable. Okay, for the next beam, so this beam has a rigid connection between the vertical and the horizontal here. So it is loaded downwards. So this has a mechanism of instability, because if we're going to load this one, the role of the roller here is just to push this beam horizontally. However, if there will be a vertical or gravity load on this, it will rotate at this direction, and there will be no other reaction to restrain that rotation or to prevent that rotation. So this is unstable. Okay. So next, we have here a beam that is supported by two external hinges. So we'll just have to reflect that there are 2 here. another 2 there, and the internal reaction coefficient for Hinge is 1. So all in all, R is equal to 4. Comparing it to C plus 3. Therefore, we have 1 plus 3, and conclude that this is 4 is equal to 4. However, again, this has a mechanism of instability, since if we are going to load that one, all of this joint will rotate. Okay? All of those joint will rotate. So therefore, we can say that this is unstable. Okay, next. For this problem, we have 2 rollers and a hinge. So we have 2 for the hinge and 1 each for these 2 rollers. So the total count of the reaction here is 4, and then we compare it to C plus 3. 4, we have no C here, so therefore 4 is greater than 3. So this is statically indeterminate to the first degree. First degree. So we'll just have to subtract the excess. Okay. So the next problem is on frame. So remember that we are going to have a criteria comparing 3B plus R and 3J plus C. So here we have to count the number of bars. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all in all, we have B is equal to 10. And then for the reaction, of course, there will be 3 reactions for each of these fixed support. So we have a reaction equivalent to 9. And for the number of joint, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 joints here. Now for C plus 3, remember that this is a pin, and the count for a pin connection has to be equal to 1. Okay? So if we have a beam here and the pin here, the C coefficient is equal to 1. Okay? Remember that this is connecting to members. Okay? It connects to members. So basically, we are going to count the number of members that this pin connects. So first, it is connecting this 2. Okay, that is 1. Another connection connecting this 2, that is 2. And another connection connecting this diagonal and this vertical here, and that is 3. So therefore, C here will be multiplied by 3, so that C here is 3. And then we just substitute now the counts. 3 times 10 plus 9, and this is 3 times 9 plus 3. So obviously this is 39, and this is 27 plus 3, that is 30, and this therefore is 39 is greater than 3. So it is obvious that this is statically indeterminate to the 9th degree. Okay, so moving on, another frame here. So we use the same criteria, 3B plus R, 3J plus C. So let us count the number of bars. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 bars here. And the number of reactions, we have 3 here, another 3 here, and we have 2 on the pin connection. So all in all, we have 2, 3, that is 6, plus 2, that is equivalent to 8. And then for the number of joints, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 number of joints. So we do not have any internal reaction here, so that is 0. So substituting now the values, we have 3 times 8 plus 8, 3 times 8 plus 0. So 8 times 3 is 24 plus 8, that is 32. Comparing to 24, 32 is greater than 24, and this is statically indeterminate to the 8th degree. Okay, so let us have another one. So we're going to count again the number of bars. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So R here is 6, 9, 12, 15. And then this should be B, okay, the number of bars. Bars should be equal to 15. And then the reaction, we have 2 each of these hinges. So we have 6 there. And then for the joints, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 joints here. 12 joints. And then we apply again our criteria for frames. We have 3, B plus R, 3, 3J plus C. Okay, so 3 times 15 plus 6, 3 times 12 plus 0. So this is 45 plus 6, that is 51. Obviously, this is 12 times 3, 36. 51 is greater than 36. And 51 is how many units greater than 36? We have 11 plus 4. So basically, we have a statically indeterminate to the 15th degree. Okay, so let us proceed to this frame wherein there will be a overhang member on the side of the beam. So if we have an overhang, our count would be just limited to a member that is supported at both ends. If an overhang is not supported at both ends and it is overhang without support on the edge, of course this will not be counted. So we are going to count now. There are 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So for the number of bars, this is equal to 15. 15. And joints, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 joints, and reaction obviously is 9. So there are 3 for each of these fixed support, so that the reaction total is 9. Again, we use the criteria 3b plus r, 3g plus c. So 3 times 15 plus 9, 3, 12, this is 0. Okay? So 15 times 3, that is 45, plus 9, that is equivalent to 40, 45 plus 9, that is equal to 54. And obviously this is 36, okay? So we have 54 is greater than 36. So 14 plus 4, that is 18. So therefore, this is statically indeterminate to the 18th degree. Okay. So another frame. So we'll just have to count the number of bars first. 3, 4, 5, 6, 7, 8. So B here is 8. Okay, for the reaction, we have 3 for the fix, 2 for the hinge, 1 for the roller. Okay, so all in all, we have a count of 3, 5 plus 1, that is 6. 6 counts of reaction. And for the joint 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 joints here. And then again, we employ this formula 3b plus r, 3j plus c. We have 3 times 8 plus 6. 3 times 8. So we have here 0. So 24 plus 6 is obviously 30. And this is 24. 30 is greater than 24. Therefore, this is statically indeterminate to the 6th degree. Okay, so moving on. This time we will have trusses. Okay, so for these trusses, starting with the first problem, of course, there will be 2 reactions here and a reaction on the roller. So therefore, we have a total count of reaction to be equal to 3. So for the number of members, this is B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have number of bars to be equal to 13. And for the number of joints, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 number of joints here. So we're going to apply the criteria for truss. B plus R is compared to 2J. So 13 plus 3, 2 times 8. So this will yield to 16, and 16 is equal to 16. Therefore, this is statically indeterminate. So next, so another truss here. So we're going to count the reactions here. We have 2 for the pin, another 2 for this, and another reaction, a single reaction for the roller. So the total number of reaction, we have 1 plus 4, that is 5. Okay, so for the number of bars, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there will be 11 bar members. And for the joints, we have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 joints here. So applying the criteria B plus R to 2J, okay, V here is 11 plus 5, 2 times 8. So we have 16 is equal to 16. So therefore, this is statically determinate. Okay. So for this problem, if we are going to analyze this one, there will be only a single reaction here, although we have a pin connection here. We cannot say that we have any vertical reaction here, because if we apply a joint section at that joint, okay, there is a single force here, this force member, okay, this force member, and this force member is restrained on this pin connection. So therefore, the pin connection will just counter a single force member, right? Okay. So if that happens, we have zero vertical force. Okay. So therefore, there will be a single reaction here. Similarly, there will be also a single reaction here and another single reaction here, because all of the pin connections will be holding a single member only, unless if we have a diagonal member here, we cannot tell that the reaction is only one. But in this case, all of the pin members holds only a single member. So therefore, it implies that the reaction shall support only the single member that is attached to it. So with that, it is obvious that this reaction will be concurrent at this point. So in that sense, that is actually a mechanism of instability. So this now is unstable. So we conclude that this truss is unstable. So moving on, for this truss, first we count the number of bars: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there are 14 bar members. So we have two reactions here, single reaction there, and another one there. So we have 1, 2, 3, 4. So we only have 4 reactions. As to the number of joints, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 joints here. So applying our criteria B plus R to 2J, we have 14 plus 4, 2 times 10. So we have 18 is less than 20. We have here unstable truss. So next, we have here another complex truss. Just the same, we're gonna count that members: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there are 14 bars. And as to the number of joints, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 joints here. And then for the reaction, obviously, we have 2 for each of these hinges. So all in all, we have a reaction of 6. So by applying now our criteria B plus R, compare it to 2J, the number of bars is 14, R is 6. So 2 times the number of joint, 10. Therefore, this is 20 is equal to 20. In this case, your truss is statically determinate. Okay? So that's it for our determinacy problem. So we will now move to determine or to calculate for reactions of the beam. Okay. So we'll start with this problem. We have a simply supported beam. We are going to determine the reactions at A and B. So of course, you know the procedure that we will just have to take moments at both supports in order to come up with the reactions, and then our check mechanism will be summation forces horizontal. So first, you need to draw the free body diagram of that. So not to waste time, I'll just copy this one, place it here, and then label the reactions. So on the hinge connection, there will be RA here, okay, and obviously there will be no horizontal force for that pin because there is no horizontal or lateral force found in the beam. So this is RB, okay. So if we have distributed loads, we can just resolve that into its resultant. So the resultant of that is located at the center of this rectangular uniformly distributed load. So 40 times 3. So it is just simply multiplying the height 40 times the base, that is 3. So we have here 120. And to reflect our distances, so of course this is 1.5, and obviously the distance the other side is also 1.5. So with that, we'll just take moments at A and equate it to 0. So 60 has a counterclockwise direction, so that is negative 60 times moment arm of 1, okay, and then 120 here would have a clockwise rotation times the moment arm, which is equal to 1.5, and then minus 120, okay, we have no moment arm because this is a couple, so do not look for the distance of that. And then RB is a negative rotation, that is counterclockwise, RB times the distance from A, that is obviously 5. This is equal to 0. So therefore, RB is equal to, so RB as computed is equal to 0. So why is that happening? So is it possible that your reaction at B do not have any force to resist? Yes, it is possible because that is what we have computed. And secondly, because of 120, this shall be lifted so that RB wouldn't have any vertical forces or vertical force to support. Okay, so we will now have an obvious reaction at A, that A shall carry all of the vertical forces now. So if upon observation, all of the downward vertical forces is 120 plus 60, that is 180. So we should have a reaction at A that is equivalent to 180. The couple here has nothing to do with the vertical forces or any horizontal forces. So do not mind this couple talking about forces vertical or horizontal forces. So let us validate that our RA should be equal to 180. So we have summation moments at B is equal to 0. We have negative 120 for that rotation. So another negative rotation, 120. So 1.5 plus 2, that is 3.5. Okay. Plus 5 RA minus 60 times 6. This is equal to 0. So computing for RA, it is really equal to 180 kilonewtons. So this will be our answers. Okay. Okay, moving on to the next problem, we have here a simply supported beam. However, the roller here is placed diagonally. So whatever the surface the roller is resting, we'll just have to create a perpendicular line to that inclined surface. So in this case, let me copy this so that we'll have a free body diagram. Anyway, copy this. Okay, so going to have here the reactions. There will be two reactions here because obviously there are horizontal components of these diagonal forces. Say this is RAY and this is RAX, and the roller, as I have said, it's gonna follow the surface where it is rested. Okay, so this is a perpendicular line there. Say this is the reaction at B. Okay, so we need also to have the slope of this reaction at B. Okay, so we need to resolve for its components. So reaction at B has to be resolved on its vertical and horizontal component. Say this is RB, RBX, and this is RBY. Okay, so let us express also the vertical components of 36. Okay, I'll just place here vertical and horizontal component. So if we project this vertical component here that is going downwards, and it is obvious that this vertical component is opposite the angle 60 degrees. So therefore, we're going to write this vertical component to be equal to 30 times sine of 60 degrees. And this one, sorry, 36, should be 36. And for the other one, we have 36 cosine of 60 degrees. Similarly, we can do resolving for the reactions at 44. So I'll just place it in here. Okay. Anyway, this is extended up to this. And our leftward force here. Okay. So I'll just label this as F44Y, and this is force 44X. So to solve for the corresponding component, we'll just have to use the slope of the 44. The slope of the 44 is 12 vertical. This is 5 horizontal. Obviously, this is 13. And then use ratio and proportion. So we can just say that F44X, and then pair this to the horizontal slope, 5. This is equal to F44Y all over. The slope of Y is 12. And then this shall be equated to 44 to the slope of the hypotenuse. And then both of these unknown variables will be connected to this side wherein we have a complete given. So F44X therefore is equal to, by cross multiplication, we have, sorry, I think this is 13, okay, 13. We have 5 all over 13 of 44. So F44Y is also equal to, by cross multiplication, that is 12 all over 13 times 44. So if we observe, we really do not need to do this one. Just remember that if we have component and the slope, you just pair your x to the horizontal slope and then divide it by the hypotenuse. So that is what has happened here. On your 44x component, the horizontal slope is 5, okay? The horizontal slope is 5. Just copy that 5 and then divide it by its diagonal or diagonal slope, that is 13. Multiply it by the mother force, that is 44. And that will be your component. So similarly for the 44y, just refer to the vertical one. So this is the vertical, and that is obviously 12 divided by the diagonal multiplied by the mother force, that is 44. So we have obtained the component here, F44x and F44y. We have here equivalent to 16.92. And for the other one, we have 40.62. Okay, so we all have now the external forces on the beam. So what is left for us to work is the diagonal RB here. So the diagonal RB there will be solved again by the vertical and horizontal slope. So if we're going to illustrate that one, this is the diagonal where the roller is placed, and then we're going to have a perpendicular component to that. See, this is the reaction at B. Okay, so this is, obviously this is 3, 4, 5 triangle. So if we are going to have the theta here, okay, we project this theta out of this triangle here. Why? Because this component is perpendicular to the surface. We need to use this triangle actually. So if this is labeled as theta, okay, we'll just use the principle we're in. If this is the theta, just make a perpendicular line and then just add a vertical line on that, and the point of intersection or the angle between them is also the angle measured from the horizontal line and the diagonal line here. So if this is the case, this is also theta. So therefore, if this is RB now, if this is RB, okay, therefore the vertical component is this one, and the horizontal component is this. Okay, so therefore this is RBX and that is RBY. Okay, so this is the right triangle now, RB being the mother force. So these are just the two legs, RBX and RBY. So writing our function to relate these components to its mother, we need to write here function of sine. We'll have an opposite component, the angle is RBX all over the hypotenuse RB. So therefore, by cross multiplication, RB is equal to, or we'll have to use RBX is equal to RB sine of theta. Now, referring to the angle theta, this is 4, 3, and 5. This is theta. Sine theta is 3 all over 5. Opposite over hypotenuse, that is 3 over 5. So RBX is 3 all over 5 of RB. Okay? So you see, we have 3/5 of RB. So this is actually the danger when we use this slope, because this slope is not directly referring to the RB that is perpendicular to this surface. So this slope is intended for the surface, but our reaction is actually perpendicular to the surface, but not the surface. Okay? So if you have to use this slope, you will be mistaken now, because if you have 3 is a vertical, or you may say that that is a horizontal one. So RBX is paired to 4 and then divided by 5. So it's obvious now that we'll be having a mistake if we're going to do that. But what if we use this slope and then say that we copy this? We have 4 horizontal, 3 vertical, and 5. Again, we are mistaken. Okay, you see the mistake. Okay, RBX is 3/5. Obviously, the slope will revert if we have a reference slope here that is referred to the slope that is inclined where the roller is uh, rested. Okay, so moving on, obviously our RBY will be cosine function RBY all over RB. Okay, and cosine is 4/5. Okay, so RBY will now be equal to RB cosine of theta, and cosine of theta is of course 4/5 of RB. Okay, so we have here a complete figure. Perhaps we can fix our figure for us to have much convenient to work with. Okay, see, this is the beam. We have already RAY and RAX here. Okay, then we have here 54, and then we have here components 36 cosine of 60, 18. So we have an 18. I'll just indicate that into a red because these are components. We have here 18 or 36 cosine 60, and then 36 sine of 60 is 31.18 going downwards. Okay, for the 44, we have here the components. We have the horizontal F44X, and this is F44Y. We have computed that one 16.92, and this is 40.62. Okay, so we are going to indicate now our RBX. This is horizontal. RBX is 3/5 of RB, and RBY is 4/5 of RB. Okay, so we now indicate all of the distances for us to finally work with this illustration. Okay, so we now take moments at A is equal to 0. We have 54 times 3.5 plus 31.18 times 9.5 plus 40.62 times 14.5, because 5 plus 6 is 11, plus 3.5 is 14.5. What else we have? Negative rotation 4/5 of RB, and that will be equal to 0. Okay, so we now compute for RB. We have 1342.75, and then for the other reaction, so we'll just place here This is point A, and that is point B. Okay, so for the other reaction, we take moments at B is equal to 0. We have a negative rotation, negative 40.62 times 2.5 minus 31.18 times 7.5 minus 54 times 13.5 plus RAY times 11, 13.5, 14, 17 times 17. By the way, I think we have also omitted here the distance of RB. So I'll just have to correct that one. So the distance of RB to A is 11 plus 6, that is 17. So this is equal to 0. So we'll just have to divide 1342.75 divided by 17. We have 78.99. So anyway, we will also check it by summation forces vertically by and by, so that we can check our solution. So next, this is now equal to 0. We have here RAY to be equal to 62.61. So I think we have to check our vertical here. So summation forces vertical is equal to 0. We have downwards 54, 31.18, downwards again. We have another downwards 40.62, and then we're gonna add the two reactions here. We have 4/5 of RB and RAY. So RAY is going up plus 62.61, and then another upwards 4/5 of 78.99. So is it equal to 0? So it is equal to 0. Okay, so therefore these are correct values of our reaction because of satisfying the other equilibrium equation, which is summation forces vertical is equal to 0. Okay, so finally we are going to determine the reaction at X, or horizontal reaction at X. So that can be done by having this third equation. So RAX is towards right, minus towards left 18, minus leftward 16.92, and another leftwards, that is 3/5 of RB is equal to 0. So we'll just have to substitute RB here, which is 78.99. So therefore you can now get the value of RAX to be equal to, we have 81.39. Sorry, 82.31. So we have 82.31 as our horizontal reaction. So finally, we can now determine the mother reaction at A, that is simply equal to square root of RA x, this is squared, and the component of y is also squared. So RA is equal to square root of 82.31 squared plus RAY 62.61 squared. So finally, we have 103.42 kilonewtons. Okay, so that's it for this problem. So we're going to have another session for the continuation of these solutions, and then additional information on our new topic later on, that is uh, trusses or analysis of trusses. Okay, so thank you for listening, and good day.